Alright, let's go. Number 10. The Bostrom Trilemma. Nick Bostrom wasn't trying to prove anything about simulations. In the late 90s, he was working on Anthropic reasoning at Oxford, the dry statistical problem of how an observer should update their beliefs given that they exist at all. It's the kind of math philosophers use to argue about doomsday scenarios and cosmic fine-tuning. Routine, abstract, nobody expected it to end anywhere near computer science. Standard assumption going in, you are a physical being in a single, base-level physical universe. Your memories correspond to real past events. There is no layer beneath this one. Philosophy had circled this idea since Descartes, but nobody had built a formal probability argument for doubting it. Then Bostrom ran the numbers on future computing power, and the assumption didn't survive contact with the math. In April 2003, Bostrom, then a researcher at the University of Oxford, published a 13-page paper titled, "Are You Living in a Computer Simulation?" in the Philosophical Quarterly. The paper doesn't claim we're simulated. It proves that at least one of three propositions has to be true. Civilizations almost always go extinct before reaching the technology to run ancestor simulations, or they reach it and choose not to run them. Or nearly every mind, with experiences like yours, is running inside one. Philosophers tried to escape the trilemma. Some argued high-fidelity simulation of consciousness is computationally impossible. Dismissed, since nothing in known physics forbids it, only current engineering. Others argued advanced civilizations would have moral objections to running ancestor simulations, dismissed, because the argument only needs one motivated program out of trillions of possible civilizations, not universal consent. David Chalmers spent an entire 2022 book, Reality Plus, extending the argument rather than refuting it. If the third branch is true, your first kiss, your mother's voice, the argument you had last week, all of it is processed, not lived. Which of the three is it? And if it's the third one, what changes about how you're allowed to answer that? The unsettling part isn't the philosophy. It's that nobody has found the exit. Alright, number 9. The Planck length pixel problem. Max Planck wasn't hunting for the texture of space-time. In 1899, he was trying to derive a system of natural units from fundamental constants, a bookkeeping problem, a way to make physics equations cleaner across different fields of study. Standard physics assumes space is continuous. Between any 2 points, infinitely many more points exist. You can zoom in forever and the universe never runs out of room to subdivide. That assumption underlies calculus, general relativity, essentially all of classical and modern physics since Newton. But when you combine quantum mechanics with gravity, the equations hit a wall at roughly 1.6 times 10 to the negative 35 meters. Below that scale, the concept of distance itself stops producing sensible answers. This isn't fringe math. It falls directly out of combining the Heisenberg uncertainty principle with Carl Schwarzschild's 1916 solution for gravitational collapse, squeeze enough energy into a small enough region, and you get a black hole instead of a measurement. Physicists call this threshold the Planck length, and it defines the smallest distance at which the word distance still means anything. Explanations were tried. Some argued it's simply a limit of measurement, not of reality. Space stays smooth underneath, we just can't probe it. That doesn't resolve why the equations themselves break down, not just our instruments. Others proposed loop quantum gravity, where space is built from discrete chunks, testable in principle, unconfirmed in practice, and never observed. String theory sidesteps the wall differently and still hasn't produced an experiment either. A minimum resolution for space is not a feature continuous physical media are supposed to have. It's a feature rendering engines have. Every object you've ever touched, including your own hand, is built from something that may not subdivide past a certain point. Nobody has explained why finite reality would need a floor. A rendered one would. Zoom in far enough, and even the ruler disagrees with you. Alright, number 8. Quantum mechanics lazy rendering. Erwin Schrödinger wasn't setting out to describe an observer-dependent universe. In the 1920s, he was trying to write a wave equation that could replace the clunky, half-finished quantum models of Bohr and Sommerfeld. A mathematical cleanup job, nothing philosophical. Classical intuition says particles have definite properties whether or not anyone checks. A ball has a position and a speed at every instant, observed or not. Physics before 1925 assumed the same held for electrons. The wave equation said otherwise. Left unmeasured, a particle doesn't occupy one position. It exists as a spread of probabilities across every position it could be in, and only resolves to a single value the instant something measures it. This is Werner Heisenberg's uncertainty principle. Formalized in his 1927 paper in Zeitschrift for Physik, later confirmed experimentally through the double-slit interference pattern that collapses into two fixed bands the moment a detector is placed at the slits. Unwatched, the particle behaves like a wave passing through both slits at once. Watched, it behaves like a single object that picked a lane. Physicists proposed hidden variables, some invisible internal property deciding the outcome in advance, so nothing is truly random. John Stuart Bell's 1964 theorem closed that door mathematically, and experiments by Allen Aspect in 1982 closed it physically. Bohr's Copenhagen interpretation just accepts the collapse without explaining its mechanism. Everett's many worlds avoids collapse by splitting reality itself, an explanation with no fewer problems than the one it replaces. A universe doesn't need to hold a fixed answer everywhere at once if nobody's checking. A rendering engine only needs to compute what's on screen. The particles making up this sentence right now, in your peripheral vision, may not have a definite state until your eyes move. What exactly counts as an observer, and has anyone ever actually caught the universe deciding? Every measurement you've ever made only confirms the answer showed up right when you asked for it. Alright, number 7, the cosmic ray computation test. Silas Bean wasn't trying to test whether we live in a simulation. At the University of Bonn, he and his collaborators Zoe Devoody and Martin Savage worked in lattice quantum chromodynamics, the standard technique physicists use to approximate the strong nuclear force by chopping spacetime into a computational grid, purely as a calculation tool, not a claim about actual reality. The working assumption in lattice QCD is that the grid is a convenient fiction. Physical space itself is smooth and continuous. The lattice is just how a computer approximates it, the way pixels approximate a photograph without the photograph being made of pixels. Bean's team noticed something uncomfortable. If the entire universe, not just their calculation, were actually built on an underlying lattice, that grid would leave a specific fingerprint in how far particles could travel before losing coherence. In a 2012 paper posted to RxIV and later published in the European Physical Journal A, Bean, Devoody, and Savage calculated that a cosmic lattice spacing would impose a hard energy ceiling on cosmic rays, and that the highest energy particles crossing that ceiling would arrive preferentially along the grid's axis instead of scattering evenly across the sky. Cubic symmetry instead of the isotropy general relativity predicts. Skeptics pointed out the known Greisen-Zatsepin-Kuzmin cutoff, observed since the 1960s, already explains the energy ceiling through interactions with the cosmic microwave background, no lattice required. Others noted the angular signature is only detectable if the lattice spacing happens to align with the GZK scale. A coincidence with no reason to be true. Nobody has ruled it out. Nobody has confirmed it either. The instrument required already exists. The telescope array and the Pierre Auger Observatory record these exact events, and nobody has published a full search for the specific asymmetry Bean's team predicted. If it's ever found, it wouldn't come from a telescope pointed at the edge of the universe. It would come from a detector pointed at the sky above your own house. The test has been sitting there, unrun, for over a decade. Alright, number 6. Digital physics and cellular automata. Edward Fredkin wasn't a physicist by training. In the 1960s at MIT, he was working on early computing architecture, trying to understand how simple, local rules, cellular automata could generate complex, unpredictable behavior from almost nothing. Physics assumes its fundamental laws are continuous, smooth differential equations, the mathematics of calculus, describing fields and forces that vary gradually rather than in discrete steps. Newton, Maxwell, and Einstein all wrote their laws this way, and quantum mechanics kept that continuous mathematical backbone even while quantizing energy. Fredkin noticed that his simple grid-based automata, obeying only local deterministic rules, could produce structures that looked remarkably like particles, conservation laws, and even relativistic behavior, without any continuous mathematics built in at all. Fredkin developed this into what he called digital physics through the 1980s and 90s, publishing his framework in the 1990 anthology paper Digital Mechanics in Physica D. Stephen Wolfram carried the idea further in his 2002 book A New Kind of Science, arguing computationally simple rules, not continuous equations, might be the deeper layer beneath known physics. Mainstream physicists objected that no cellular automaton has ever reproduced quantum entanglement correctly, a phenomenon requiring correlations that simple local rules struggle to generate. Others pointed out Fredkin's automata have never made a single falsifiable tested prediction beyond resembling known physics after the fact. Resemblance isn't derivation. Wolfram's own 2020 physics project has yet to produce a confirmed experimental result. Nobody has proven digital physics wrong. They've only shown it hasn't yet been proven necessary. If the universe runs on local update rules instead of continuous law, then somewhere beneath the atoms in your bloodstream, something is executing a step. And then the next one. And then the next one. Is physics describing reality, or describing what the rules output when run? Alright, number 5, the universal speed limit. Einstein wasn't hunting for a cosmic speed limit either. In 1905, he was trying to resolve a contradiction between Newtonian mechanics and Maxwell's equations of electromagnetism, two branches of established physics that quietly disagreed with each other about what a moving observer would measure. Newtonian intuition says velocities simply add. Throw a ball forward from a moving train, and its speed relative to the ground is the train's speed plus the ball's speed. No ceiling, no exception. Einstein's special relativity, published in Annalen der Physik in 1905, showed velocities don't add that way once you approach the speed of light. No signal, no object, no information of any kind can exceed roughly 299,792,458 meters per second, full stop, regardless of the reference frame. This isn't a measured coincidence. Einstein derived it from requiring Maxwell's equations to look identical in every reference frame, and every experiment since, muon decay rates. Particle accelerator results, GP satellite corrections, has confirmed the number to extraordinary precision. Physicists have asked why this particular ceiling exists rather than some other value, or none at all. General relativity treats it as a built-in geometric feature of spacetime, not something derived from anything deeper. String theory and quantum gravity attempts have tried to explain it from first principles and decades later still return it as an assumption rather than a consequence. A universal cap on how fast information propagates is exactly the artifact you'd expect from a system with a maximum data transfer rate between processing nodes. Every signal traveling from your eyes to your brain, and every signal your brain sends back to your hand, is bound by the same unexplained ceiling that governs light crossing a galaxy. Nobody has ever explained why the limit is a limit, only that it holds. Alright, number 4. Anthropic selection bias. Brandon Carter wasn't trying to build an argument for simulated minds. In 1973, at a symposium marking Copernicus's 500th birthday, he was addressing a much narrower problem: why cosmologists kept forgetting that measurements of the universe are inevitably made by observers who can only exist under certain conditions. The ordinary intuition in science is that you are a randomly chosen example of whatever category you belong to. A typical human, a typical observer, no special weighting attached to your specific situation. Carter's anthropic principle broke that assumption. If some property is a precondition for any observer to exist at all, like the universe's fine-tuned constants, or, as Bostrom would later extend it, like the ratio between simulated minds and unsimulated ones, then observers are never a random sample. They're a filtered one. Carter published the framework in the 1974 Proceedings paper Large Number Coincidences and the Anthropic Principle in Cosmology. Bostrom, building directly on Carter's reasoning in his 2002 book Anthropic Bias, applied the same filtering logic to simulated observers. If advanced civilizations run even a modest number of ancestor simulations, simulated minds vastly outnumber unsimulated ones, and a randomly selected observer is statistically more likely to be one of them. Critics have argued the reference class of observers like you is too vague to compute a real probability from, a fair objection, and one Bostrom himself has acknowledged without resolving. Others argue the whole approach smuggles in unproven assumptions about how common advanced civilizations are in the first place. Nobody has found a version of the argument that produces a low probability of being simulated. Only versions that argue the question can't be answered at all. If simulated minds outnumber physical ones by any significant margin, the honest starting assumption about your own existence tips somewhere you didn't choose. You didn't get to pick which category of observer you'd turn out to be. Alright, number 3. No falsification path yet. Karl Popper wasn't thinking about simulation theory. In the 1930s, he was trying to solve the demarcation problem. How to distinguish real science from ideas that merely sound scientific, a philosophical dispute over what counted as a legitimate theory at all. Standard scientific method assumes any serious hypothesis must, in principle, be falsifiable. There must exist some observation that, if made, would prove the idea wrong. Popper laid this out in his 1934 book Logik der Forschung, and it's remained the working standard in physics ever since. The simulation hypothesis runs directly into that standard and doesn't clear it. If a simulation is sufficiently advanced, any anomaly researchers might detect, a lattice signature in cosmic rays, an inconsistency in a physical constant, could always be patched by the simulators, or explained away as a limitation of the simulated observer's own instruments. Physicist Sabine Hossenfelder and others have argued in public commentary through the 2010s and 2020s that this makes the hypothesis structurally unfalsifiable in the same category as many multiverse proposals, logically coherent, scientifically untestable, permanently unresolved by observation. Bostrom's defenders respond that Bean's cosmic ray test and similar proposals do offer falsifiable predictions, at least for one specific version of the simulation scenario. Critics reply that a null result only rules out that one version, not the underlying hypothesis itself, since an infinite number of untested simulation architectures remain available. Neither side has closed the argument. An idea immune to disproof isn't automatically true. But an idea immune to disproof also never goes away. Every test scientists have run has come back consistent with normal physics, and also, exactly as predicted, consistent with a simulation good enough to hide it. If no experiment can ever settle it. What does it mean that the question still won't leave the field alone? Alright, number 2. Error-correcting code in the equations of supersymmetry. Sylvester James Gates wasn't looking for computer code. In the mid-1990s at the University of Maryland, he was trying to solve an unglamorous bookkeeping problem in supersymmetry, matching up the number of bosons and fermions in his equations so the underlying symmetry balanced correctly on paper. The standard assumption in theoretical physics is that the mathematics describing particles is purely mathematical, abstract structure with no connection to anything resembling computer science or information theory embedded inside it. To visualize the balancing problem, Gates and his collaborators built graphical tools they named adinkras, after a West African symbol for change. Studying the internal structure of these adinkras, the team found something they hadn't gone looking for at all. In a series of papers beginning around 2008 with collaborators Doran, Faux, Iga, and Landweber, Gates identified that the equations of supersymmetry contain structures mathematically identical to what are called doubly even, self-dual, linear binary error, correcting block codes, the same category of code browsers and hard drives used to detect and repair corrupted data. Gates has been careful in public statements to call the interpretation open, not proven. Some physicists argue the codes are a mathematical coincidence, an artifact of how supersymmetric representation theory happens to be structured, with no deeper implication required. Others note error-correcting structures generally exist because something built them for a reason. In biology, evolution installs them to protect genetic information from corruption. Nobody has identified an equivalent evolutionary process for the laws of physics themselves. Gates has publicly posed the question himself. Could it be that codes, in some deep and fundamental way, control the structure of our reality? If the equations describing the particles inside your own cells contain error correction, something was apparently worth protecting from corruption. Nobody has explained who or what that protection was ever for. Alright, number 1. The uncomfortable implication. None of the physicists in this list set out to threaten the concept of an unmediated universe. Bostrom was doing anthropic statistics. Bean was doing nuclear theory. Gates was balancing supersymmetric equations. Fredkin was designing computer architecture. Every single one of them was solving a narrow, technical, unglamorous problem, and every single one of them stumbled into the same unsettling shape. The standard assumption underneath all of physics is that the laws are the deepest layer, that asking why do the laws work this way eventually bottoms out in brute mathematical fact, with no further question to ask. What stumbled out instead, across a dozen unrelated subfields, was a pattern, a minimum resolution to space, a rendering behavior in quantum measurement, an energy cutoff with a predicted directional signature, a maximum data transfer speed, and error-correcting code sitting inside the mathematics of matter itself. No individual finding proves anything. The accumulation is what unsettles. If Bostrom's trilemma holds even approximately, the honest anthropic conclusion is that a randomly selected observer is more likely simulated than not. Not certain, not proven, but no longer safely dismissible either. Every explanation offered so far explains away one piece at a time. None of them explain why the pieces keep resembling each other. If reality is computational, the question stops being what are the laws of physics and becomes who or what is running the program, and whether that question is even answerable from inside it. None of these 10 findings are fringe. They sit inside published, peer-reviewed physics, sourced from Oxford, Bonn, Maryland, and MIT. The universe is not confused. The equations are not broken. The unsettling part is that our most tested, most successful theories keep pointing at the same door, and nobody currently working in physics can tell you what's behind it. If you want to see more videos like this, click the video on screen now.